Good evening and welcome back to Vegas October 1 Sounds. Yep, my voice is back and I'm ready to cook and start rolling again. So, where'd we leave off? The last two videos that I published outside of the telling you I was a little under the weather related to doing an exploration on a single sound across multiple videos and asking the question, was that a sniper that produced those sounds? And got real excited and real interested in finding a sniper. But after a little consideration, I determined that I really didn't know precisely where the shot was coming from. It didn't follow the normal patterns, and therefore I needed to do more analysis. And the first thing that I would normally do is lay out in time the sounds from each of the video. That is, for regular sounds, the time of arrival of that sound in the video in global absolute time might indicate from which direction the sound is coming from, and therefore identify at least partially the nature of the source of the sound. So that's where we're going to start this evening. But before we do so, we have to start asking some serious and very critical questions. There's going to be a little bit of graphics tonight. There's going to be a little bit of math. And what you're going to come away with is a far deeper understanding of what the supersonic shock wave front is, and the nature of how the sound arrives at an observer, and a deeper understanding of how it's created and how it propagates throughout space and time. So, let's start back with some very basic principles. And to do that, I'm going to hop over to a different desktop here and start drawing a few pictures. So, if we have a source of sound, much like, let's use the muzzle blast from a gun, or perhaps snapping your fingers. Both of those are types of sounds that propagate as though they were point sources, namely they come from one spot in space and time. And because of that, they have a propagation pattern that resembles a sphere. That is, they propagate out in all directions at an even rate based upon the speed of sound in the local area that they occur. So, from a two-dimensional perspective, if you were to record the sounds at every, let's say, a period every tenth of a second or something, you would see that they progress outwards in nice, evenly spaced concentric circles. Now, I know my drawing isn't perfect and it doesn't look like evenly spaced, but the distance between the sound start and the first measurement at a tenth of a second, that distance would be the same as this distance, would be the same as the third tenth of a second, and out until you could no longer hear the sound. And that is a sphere, and this is a 2D representation of it. Now, why do we start with a 2D representation? Because it's kind of easy to understand, and the software I have on here doesn't easily let me represent a sphere. But let's view it from a different perspective. Let's erase those little lines and say, rather than looking at it from an overhead perspective with the ground underneath, let's look at it from the side, and let's put a ground. Let's say, put the ground down here, and the source, well, let's make it realistic. Let's erase all that. Let's start a little simpler than that. Let's say that we have the ground right here. Alright? And we have a sound that occurs at ground level right there. And that sound being a point source, i.e., let's say a muzzle blast or snapping of fingers, or anything else that creates a point source, produces a sphere that propagates out. Okay, now when you look at this sphere, it intersects the ground. And so if you would turn this 90 degrees and look at it from the ground perspective, so let's say this is the ground, and now you're flying a plane over that point, then once again you'd see these concentric circles, because the plane of the Earth intercepts a sphere in circles. That makes sense? Well, I hope it does. So the side view and the elevation top view are essentially the same when the plane of the ground intercepts the expanding sphere, which is at ground level. Not so if it's above the Earth. So in this case, where we have a source of sound that is above the, well, let's make the ground a little lower because we're going to want to be doing things. So let's put the ground lower, and then we're going to put a source of sound that's above the ground. Okay, now once again, this is a point source, so it expands out in a sphere. That's just a model. How it really expands can be complicated, and as it expands, every 1/10 of a second, that sphere hasn't hit the ground. And what we want to know is what the pattern of sound is on the ground, because really that's where most of the action occurs, both in Vegas and anywhere else. We don't have people hanging out in midair to listen to all the sounds. So it takes a while for that sound to go from whatever elevation it is down to the ground. But when it eventually reaches there, the first sound that will hit is like that, and that'll be the point at which the ground intercepts the first wave, and then 1/10 of a second later it will intercept another wave somewhere out here. Another 1/10 of a second it will intercept another wave out here, and so on and so forth. Now, the distance between these points is not evenly spaced, because the time of arrival at each point is a function of the distance traveled divided by the speed of sound. And as you can see, each little tick, the distance traveled is greater, because the path is longer, which is normally the case. But how do we calculate that length? Well, to calculate the length, we essentially have to measure the distance from the point of origin of the sound to the Earth, which is the elevation, and then we measure the distance out to whatever point is that we're looking at. And so that distance, which we'll call d, is equal to the square root of now we have to put on some labels here, so let's call this little d, and this little actually let's call that little e. E for elevation. And then let's call this x. So in this case, we would say that e squared, which I'm sure you all know what squared means, plus x squared, and then you take the square root of it, and that would give you the length d for any one of these. Alright, so now we have an understanding, and we call that the Euclidean distance, or Pythagorean distance, whichever you want. And forgive my spelling if it's wrong. Now this is all fine and dandy. So we now have the ability to understand, for an elevated source, that the time of arrival of the sound at any specific point is a function of both its distance along the ground and the elevation of the source itself. Okay, and that distance is given by this simple mathematical formula. Now we could pull up Google Maps and attempt to measure that directly so that we don't have to go through that calculation, and we will later in this session. But before I get there, what we're going to be asking this evening is, what would we expect the time of arrival for a sound caused by a sniper to be at particular locations? And in particular, if that sound is the sound of the supersonic crack, when do we expect that in time to arrive at a particular point? And that will be the net result of this video this evening. But we have to start simple, and this is the muzzle blast, or a point source, because the supersonic crack is not a point source, and I'll explain that in a minute. Alright, so we've got this elevated sound up there, and now we can go along and we can measure each of these distances for x for each thing and calculate the time of arrival at it. And when we do, and we plot it out, then what we get is something that looks like this. Now this is on the ground. You have, like before, we have the ground in the back, but now we're flying a plane overhead, we're looking down at the ground, and we want to see what the time of arrival of these things are. And what we'll end up with is a set at specific times. We'll end up with, again, concentric circles, and that's a 4. Wrong one. Let me put the green back in. Alright. So what we'll get are concentric circles. But rather than being evenly spaced, they'll be circles, and I'll explain this a little bit better here in a second. Now that might look evenly spaced because I'm a poor drawing, but what is happening is that the distance here is greater than this distance, which is greater than this distance, which is greater than that distance. So that's only a little bit depending upon the elevation. So on the ground, looking from above, the time of arrival of the muzzle blast is not uniformly distributed across the ground if you're shooting from an elevated position. If you're shooting on the ground, then those spacings between each of the rings is equally spaced. So if you're on the ground and you have two observers and you ask what the separation and time of them is, or what is the time of arrival delta between person A and person B, you can't simply take the distance and divide by the speed of the sound, because the distance traveled from the source to the observer are these pink lines and not the line along X. But there is a relationship, obviously, and you could calculate that based upon the speed of sound and the elevation and the distances along X mathematically, and we'll do that later. But the important thing to notice is that the sound from an elevated muzzle blast does not reach people who are separated by equal distance in equal times, or inversely, if you measure the distance along here in equal times, it does not produce equal distance for an elevated sound source. It does if the sound source is on the ground, because there's no E component then, no elevation to it, and this equation up there simply becomes x squared, which the square root of x squared is x, so it's x is x. Alright, so that's a point source, and it's a fairly easy thing to ask. And when you're listening to these sounds, if you can find the muzzle blasts, then you could ask these questions of, okay, when would I expect the muzzle blast to arrive if I'm on the east side of the venue versus when it arrived on the west side. But again, it's not simply the distance between the east and the west side, it's the pink distances. You have to know roughly what the elevation is. However, if you were to take a bunch of videos and measure all the time of arrivals, presuming of course that you could arrange to have all the videos synchronized, which in and of itself is a monumental feat, then you would see a pattern not of equally spaced concentric spheres if it was an elevated position, but of unequally spaced concentric circles, rather, not spheres. So right quickly, if you plot out all the times of arrivals of the muzzle blast, and it turns out to be perfectly symmetrical concentric circles, then you know you have a shooter on the ground. Correspondingly, if it's not, and the times of arrivals are unequally spaced, then you have an elevated position. Now that's of course presuming you have enough videos and enough samples to plot it out. Now why do I say that? Because I've done something like that for the lag. And the lag, as you remember, is simply the difference between the time arrival of the muzzle blast and the time arrival of the shockwave, with the shockwave almost always arriving first. And if we were to go back over here to my other desktop, and I will refresh your memory, here I do a contour plot. I did exactly what we were just talking about, but rather than just measuring the muzzle blast, I measure the time of arrival difference between the muzzle blast and the supersonic crack for all the volleys that evening. Now in this case I don't have too many data points, but it's enough to give me a general idea of what the lag will be for those volley rounds throughout the entire region. And we could create a graph like this for the muzzle, and what we would expect to see would be concentric circles originating at the source, unequally spaced along the ground, with the distance between the concentric circles getting smaller as we head out until they reach a point at which they don't go to zero. They go to the approach of fixed distance, because the elevation has less and less effect on the total sound path traveled along those purple lines. All right, but back over to our sketch situation. All right, so that's the nature of the muzzle blast. Now, sound, not all sounds are point sources. Not all sounds can be modeled as point sources. There are many different ways in which shapes and forms that sounds are produced. For example, if you drop a long log into a body of water, what you'll get is what we call a line source. That is, the displacement in the water of the log creates waves coming from both sides of the log that are essentially parallel to the log for the length of the log. Now on the ends that's a little bit funnier, but with the bullet we have to talk about something else. So let's start talking about the bullet and the sounds. And notice I used plural because it produces lots of sounds. Let's talk about, once again, the supersonic crack, because after all, that was the sounds that we were measuring in the last two videos for the supposed sniper. And we were going to ask the question, well, if we plot the times of arrival of those sounds, can we tell where the source of the sniper is? And I will answer that question before the evening is through. All right, so if we have, once again, the ground, all right, and if we fire a bullet, obviously they're almost always above the ground because otherwise the bullet doesn't get too far, parallel to the plane of the earth. Then all along the path of the bullet, it being a supersonic projectile, is emitting is a bad word, but is pushing the gases away from the bullet, and in so doing it creates a compressed region of air ahead of the bullet, and then that flows around the bullet, and then as it passes by the tail of the bullet, the gases that were compressed expand back out into a lower pressure region, creating, and that whole phenomena we call shock wave. And so those shock waves, which are continually produced, even though they do have discrete elements to them, can be modeled as not modeled as, it produces a conic shaped wavefront. And this is a 2D representation of a 3D phenomena. Okay, and that cone, in which these leading edges are straight lines all along the edge of the cone, all around the cone, are what we hear as an observer when it passes by us. So when that wavefront reaches us, we hear the snap sound. So let's discuss in detail what that really means. So what happens if we have the ground? What happens when that cone intercepts the ground? Okay, well now this model isn't too good, but what I'm going to do is bring up an image that will give us a clearer understanding of it. And you'll notice now here that the cone is traveling actually, or being created in parallel to the plane of the Earth, so that this plane of the Earth intercepts the cone parallel to the trajectory of the bullet. Now that's, not how bullets really work, but we'll get into that in a few minutes. So we go back over to my other desktop, and we just go over to the Wikipedia. Then we see that this cone, which is pointing up instead of going right, when the plane of the Earth intercepts it, it intercepts it in a hyperbola. So the sound is heard on the Earth by the observers in this hyperbolic form that is at the, I guess I need to draw a little bit on this, don't I? At the place where we are, if you're directly under the bullet path, then you hear the sound very early, and if you're not, if you're further away from the center of the bullet, then you hear it later. And even though you're at the same exact position, you'll only the people at the center or right underneath the bullet hear it first, and then people 100 yards on either side of you will hear it at a later time. If the bullet was headed directly towards the Earth, i.e. you were firing down at a 90-degree angle, then it would form a circle on the ground, i.e. it would propagate in a manner in time and space much like a muzzle blast does when it intercepts the ground, except these would be perfectly concentric circles, evenly spaced. So the angle of that cone relative to the Earth is going to determine exactly which shape you see on the ground. Okay, so let's go back over to the drawing side and think about that a moment. So here we've got this cone, and it's traveling along. So let's look at this from a top perspective. Let's look at it as though we're flying over things. So what we're going to do here is, this is the Earth. We're flying over the Earth, and just for sakes, we see, if we could see it, a bullet is traveling along like that. And if we could see it, it would be making, if the bullet's right here, then it's left behind it this cone. If it's Mach 2 or 3, let's say the angle is approximate. And if we have an observer here, very close or at the origin of the bullet there, and we're going to have 3 observers where these blue dots are, and we're going to call them A, B, and C. Now we know from our little train again, we know from our little diagram earlier that the pattern of arrival of the sound is kind of like this. It's not a circle, it's a hyperbolic, because we're traveling parallel. Okay, well, what does that mean? Well, that means that at some point in time, B heard the sound before A and C, and then the sound traveled a little further and propagated out and eventually reached A. So B will hear the supersonic crack before A and C, simply based upon the fact that the crack has to propagate from the point at which it's created, which is along the path of the bullet to points A and B. And you can say, well, how much? How long? Okay, so the faster the bullet, the greater that time difference is. The slower the bullet, let's say if we were to travel Mach 1 or be at the speed of the bullet, then this cone would become flat like that. And it would be just like the log scenario where everybody who's positioned up and down at the same location would hear the wave at the same time. Now, of course, from left to right, people further along would hear it at a later time, and blah, blah, blah. But back to this parabolic thing. So just like when a jet flies overhead, those people directly under the jet will hear the sound first compared to those people who are a mile or two either side of the people directly under the jet. And that's simply because of the shape of this cone intercepting the Earth, which creates a hyperbolic shape. As the bullet, goes out further and further, the cone starts to widen out, and also the trajectory starts to go more towards the Earth, and this whole cone bends to where you'll get, first it starts out like that, and that kind of is like this, then it gets a little wider like that, and eventually it gets to the point where it's probably pointing very close to the Earth, or actually like that, and creating circles. So these are circles. These would be hyperbolas. There would be probably some ellipses in here, and maybe a parabola here. So as you can see, as the bullet, when it travels out, the shape on the ground will change. But we're going to ignore those nuances for now and talk about precisely what expectations for the time of arrival of the shock wave we would have for observers. Alright, so we've got observers A, B, and C. And the bullet gets launched, and we can eliminate these little parabolic forms for now. Alrighty. So when the bullet's back here and it passes point B, and point B gets hit or hears the sound, it's going to hear it right along the path of the bullet. And then that sound will propagate the distance from A to B at the speed of sound. And so the time at which A hears it, so we're going to put the time of arrival for the shock wave at point A is equal to the time at which we hear it at point B, which we'll call, we can just call it time at B, plus the distance, which we'll call lowercase d in this case, d, over the speed of sound, which we'll call c naught, which is c naught. Alright, and if c is at the same distance as A, then it's going to have the exact same time of arrival formula. So, all we have to know is the distance from A to B, in this case, and the speed of sound, and the initial time of the bullet, and we can calculate when it arrives. Easy peasy, right? Yeah, okay, well, don't get your hopes up so far. But the point is that depending upon where you're at, it's not going to be an intuitive situation. It's not going to follow the same as the muzzle blast. You'll have to know a few more things, and to explain that in depth, I'm going to give you a side perspective now. So let's take another example. So let's erase all this crud. And once again, we're going to draw some ground. Ground's down here. A bullet comes along up there. It's got this cone. And but first, let's label where our observers are. Let's see. Let's make it a little easier than that. Let's go back and stick with an overhead view. We've got a bullet, and we're flying a plane once again. We're looking down on it. Bullets going that direction. The ground is behind us, all everywhere, or below us, I should say. And we've got an observer here, point A, and it's a distance of D away from the bullet, D. And then we're going to have another observer along the path of the bullet. Now this is overhead view, somewhere here, very, very close, so that the distance between the bullet and this point of B is essentially 0. So now we're going to calculate the time of arrival of the shock wave. Well, the shock wave that B hears is the one that's produced very, very close to it. Okay, so when did that arrive? Well, that shock wave was created at, let's say the bullet started right here, okay, just for sake of argument. Then the bullet traveled this distance, and we'll call that L. So the time it takes for the bullet to travel that is L over the speed of the bullet, V. And so the observer at B will hear the shock wave at approximately L over V. And the observer at A will hear that shock wave, which is created here, because that's the shortest path to it. In this case, because the bullet starts there, it's not exactly the case, but close enough. I've got to make sure I'm doing this correctly. Yeah, we have to add a few more caveats to this before it's accurate. In this case, it has to be the case that the bullet is fired out of the gun exactly there. Okay, because otherwise the math changes. So if the gun is located right here, and the bullet comes out, and we have an observer A up there, then the first opportunity for that to hear a shock wave produced by the bullet flying out is the point at which it leaves the barrel of the gun. And so the shortest distance, which is what determines when you hear it, will be the distance from A to B. So the math that I'm going to give you here will only work if we have an observer which is at the barrel of the gun but at a cross distance of distance D. So in that case, then the time at which it hears the sonic wave will be D over the speed of sound. And so now we can make a comparison between these two things such that we have 3 cases here. And I need to get rid of the green so that we can have some writing room. There we go. So we have 3 cases. We have the distance D, the time D over C naught equal to L over V. In which case, both observers A and B will hear the supersonic crack at the same time. Well, you say, well, what's distance L? Well, that depends upon the speed of the bullet. If the speed of the bullet is twice the speed of sound, then this L could be, for this equation to hold to be true, then that would mean that L would be 2 times D. Or if we have bullet traveling at Mach 2. The Mach number, 2m. In that case, and then L is 2 times D, so we can scratch off L and put 2D. I'm doing that wrong. I'll get it here in a minute. Here we go. If the bullet is traveling at twice the speed of sound, then it covers twice the distance. And for the times of arrivals to be equal, then L has to be twice D. Make sense? So, in this particular example, you can have somebody that's down away from the gun at let's just say 300 feet. Now let's make it 400 feet. And somebody at 200 feet away, and yet they hear the shock wave at the exact same time. Now you need to get that through your head. That you have somebody who's further away from the gun than another person, but they'll hear the shock wave at exactly the same time. And if we were to plot the cone out here, let's plot the cone in green, then what we'd see is this is the cone. Okay, and anybody along the front of this cone is going to hear the Mach snap, or excuse me, the supersonic crack at exactly the same time. So anybody parallel to the front of that cone with the same distance away from it is going to hear it at the same time, simply because of the speed of the bullet relative to the ratio of the speed of sound. So let's take a different example. Let's take one where we have two observers. We have two observers out here, way the heck out there. One there and one there. When do they hear the supersonic crack? Well, they too hear it at the same time, because the distance between the bullet path and them is so small that there's no propagation delay, and since they both have this distance, then they hear it at the same time. Okay, now, so case number 2. What's the case number 2? If B is out here a little further, where that means that rather than equals, we have the time at A is less than the other, then obviously if this is greater than 2L, then B, if the observer out there will hear the shock wave a little later, but not much more than A, not much more. Okay, and if it's shorter than 2L, then let's say we put an observer right here, we'll call them delta. And they're only half the distance of D. Then in fact, they will hear that at 1/2 the time earlier than D. Which, that would follow the normal thing. If you're closer, you're going to hear it earlier. But anything to the right of that, greater than 1D, it wouldn't follow the logical reasoning. And that's where we're going to get to. It's here. If you're listening to just the sonic cracks, you have to know bullet speed and the source of the bullet and the speed of sound and the distance away from the bullet path to make any reasonable determination. So let's go ahead and drop right into the observations that we were making from the sniper. Only let's not use the sniper ones because there's too many variables there. Let's do the same calculations we would do for the sniper, except with the 223 rounds coming from somewhere near the Mandalay Bay. So if we go back over to our other desktop, then what we're going to do is pick some spots throughout the venue, and I need to make this bigger, don't I? Yeah. So what I'm going to do is take volley 9, and I'm going to take volley 9 consists of three bursts. One short one on the front, a short one on the end, and the long one in the middle. And I'm going to take the first shot of the burst in the middle of volley 9. And I take volley 9 because there's just so many occurrences of it. And I'm going to take 1, 2, 3, 4, 5, 6, 7, 8, 9 different videos. And I'm going to measure two things from those videos. Or from the videos, I'm going to measure one thing. I'm going to measure the lag. So the lag is simply noting when the muzzle blast occurs, when the supersonic crack is heard, and taking the time difference between them. And I'll show you on the map where these are, but first let me tell you. Oasis is the Oasis Apartments. Hebrew is the two ladies speaking what I think is Hebrew in the Luxor parking lot. The bus is the Mandalay bus stop. Across is the guy on top of the trailer near the VIP West. And he's kind of looking around talking about cops and all that. Under occurs is a location near the front of the stage, down low, center. And they're by those lattice work that kind of makes them look like they're under. Ray is Raymond Page. Now Raymond Page moves around, but at the time of the first shot of 9B-1, he's at gate 2B, I believe. Dan Blazarian, he also runs around. At the time that volley 9 occurs, he's over by the Oasis Apartments, except much further north than the Oasis recording. And once again, I'll show you. Both the west wall and 24 under cop cam 24 under 387 occur on the west side of the venue near Cop Corner. They're very close to the intersection of Mandalay Bay and the Boulevard. And so these two are very close together. And so I would expect the results for them. Then what I do is I go over to Google Maps and I measure the distance from the base of Mandalay Bay to each of those points. So let's go look at that for all of those, so that you'll know what I'm talking about. So let's identify them first. Alright. Do I really need that? No. Alright. So first we'll identify Oasis Apartments. It's over here. This is Oasis Apartments. Next I'll identify Dan. And when Dan was running his little line of travel, if I can click on it here, is there. And when he was doing it, I believe he was right there. So that's Dan. Next we'll go left over here, or west to the bus stop. That's the Mandalay bus stop. Then we'll go up to the Luxor parking lot, which is the Hebrew one, which is there. Then we'll go way up to gate 2 for the Raymond Page, somewhere up in this area. Okay, then we'll go to Cop Corner. And we have 3 of them here. One is the guy, that's the across one, standing on that trailer there. Another one is the cop. Let's see if I can get that highlighted. Well, anyway, the cop was right about in here, between this one and this one. And then the other people were over here near the wall. So let's see, did that cover them all? Oh, under, we still have under to do. Okay, and under occurs right here. So we have a good sampling across various places. It kind of simulates the sniper, which had, various different places. Okay, then what I would do is go over to Google Maps and measure the distance with this, so I don't have to do it. And you notice that I'm measuring from the base of Mandalay Bay to, in this place, I'm measuring where the cop was, and the distance is 753 feet, so I should have 753 yes for the cop. And I did that for each one of them. Now that gives me the ground distance. It doesn't give me the Euclidean distance. And I'm going to calculate the Euclidean distance. So I create myself an Excel spreadsheet with these numbers in them. And then I go over to my programming environment. And what I do is I write a little program, and goes in and I set the elevation to room 32,135. It's 331 feet above where I was measuring the base to. I set the speed of sound to be 1,138 feet per second. Then I read in my Excel spreadsheet, and then I start calculating. In this case, I'm going to calculate easy for you to say, Euclidean distance. And remember, that's the ground distance squared plus the elevation squared, and you take the square root of it, and you have the distance that the sound from the gun to the observer must travel for the muzzle blast. So we calculate that and convert it to integers, since I don't want all the extra digits. And then to calculate the time of arrival of the muzzle blast, you simply take that Euclidean distance and divide it by the speed of sound. And then, since we've measured the lag as the difference in time of arrival between the muzzle blast and the supersonic crack, then all we have to do is take the time of arrival of the muzzle blast and subtract out the lag, and we've got the difference. And so now we've calculated the actual distance that sound travels between Mandalay Bay and the observer, and then we have calculated the time it takes for the speed of sound, and then we have when the supersonic crack arrives, not based upon a long complicated formula, but based upon the observation of lag. Okay, and then I format them, and then I sort them by the distance, Euclidean distance, and then I sort them by the time of arrival of the shock wave, and then out comes these numbers. So first, let's talk about Euclidean distance. So the distance on the ground is d, the Euclidean distance is e, and these are the IDs and everything. And in this case, since it's sorted by Euclidean distance, it goes from smallest to largest in ascending order. And so the closest place, Euclidean distance, was the bus stop, and the next was the ladies in the Luxor parking lot, and the next was the cops on the corner, and then just a few feet away from them, tens of feet away from them, were the citizens who were hunkered down next to the wall. And then after that came the guy on top of the maybe it was a restroom or something there by the VIP tent area, and then the next furthest away was the center of the stage, Raymond Page, Dan, and finally Oasis, and you can see all the distances. And you'll notice that the Euclidean distance and the distance on the ground are in the same order, but what you need to look at carefully is how much the elevation contributed or extended the distance over from D to E. So in the case of the bus, where you're close to the Mandalay Bay, the elevation of the shooting location has a greater impact. And remember that the separation between the concentric circles are large closer you get to the source. So in this case, we would expect, let's see, what's the difference? From 452 to 560 is 108. Whereas down here, since you're much further away, then the contribution of the elevation to the overall path is going to be smaller. So 108 at the top, and on the bottom we've got 34. So as you can see, the further away from the shooting source you get, the closer those concentric rings get. But it's not a tremendous change, but it is observable. All right. So, and of course, since the speed of sound is constant, the time of arrival of the muzzle blast is given simply by the E over the speed of sound, and that's in this column called muzzle. And as you can see, if you sort them by Euclidean distance, then the time of arrival of the muzzle blast is also sorted nice and equally. So if you're listening to muzzle blasts and you've got them all recorded based upon an absolute finite clock, which again is a tricky thing to do accurately, then the most furthest away person would hear the sound last. Alright, so then we go over here to the interesting part, and this gets down to the nature of the question we're going to ask, and that's the time of arrival of the supersonic crack. So, we look at them, and immediately we notice that it goes 0.4, 0.5, back down to 0.4, then up to 0.5, and then over here these last ones look like they're kind of in order. So, if we sort on Euclidean distance, then the shock waves don't necessarily follow that order. And that's because, as I explained earlier, the shock wave arrival time consists of two components: the bullet time and the propagation time from the bullet path to the observer. And I didn't show you the entire formula because I wanted to make it simple, so I showed you simple examples. But immediately we observe that if we were to ask the following question: which sound do we hear first, and is that one closer to the source, indicating where the sniper might be located? And the answer is you don't know. You don't know, because in this example, this is a real example, these are real bullets. You can see that, let's take an example. The time of arrival of the ladies at the parking lot for the shockwave was half a second, and they're at 700 feet traveling time. Okay, but over here at let's see, at 866 feet, which is an additional, what is that, 260, let's just say 260 feet further away, you have the supersonic crack getting there earlier. And that's simply the fact that the bullet is traveling faster and the recording position is closer to that center line of the bullet path. That is, the recording location is much closer to the bullet path. And you know that how it does that could be any number of ways. It could be closer in height, it could be closer in X, it could be closer in Y. All those things are a contributing factor. Okay, so let's take another one. So here we have somebody out there in the middle of the stage at 1,000, roughly 1,100 feet, and the supersonic crack arrives there at 0.529 seconds. But yet that's the same as somebody at 700 feet over there in the Luxor parking lot. And you say, how can that be? And this one's a real good example, because with the Hebrew ladies, they're at such a large angle to the direction. The bullet comes out from the Mandalay Bay window. It heads over towards the venue, and that's the path of the bullet. But the lady recording the sounds is in the Luxor parking lot is, like 60 degrees, let's say, separated from the path of the bullet. And at that distance, the shock wave that she hears over there was generated almost nearly at the muzzle. So it's propagating away from the muzzle at the speed of sound. That's slow. Whereas the people over here in the stage, who are much, much closer to the bullet path, the bullet gets out there quick, because it's probably starting out at faster than Mach 3, so it's traveling 3 times the distance, and it's slowing down along as it goes. And so it gets out there much, much quicker. And so the crack gets there close, quicker, almost first. So it's that fact that where the crack is generated along the bullet path that you hear, and the fact that it propagates away from the center line at the speed of sound, but the whole cone is generated at the speed of the bullet, that has to be taken into account. So the answer to the question, if we plot those sounds on an absolute time scale for those 5 sniper sonic cracks that I observed, we won't be able to tell shit by which one arrived first, basically. So I'm going to have to take those numbers and I'm going to have to plug them into a complicated formula to come up with a possible distance from which those 3 things, if it's even possible to calculate. So let me put this to you another way. Asking the question, or making the statement that because a supersonic crack arrives first, we must be that's a bad way of putting it. If it takes longer for the crack to get to us, then we're further away from the source. No. We're further away from the bullet path than the source. Now that's a simplification. That's not always true, but that's, more dominant. So we can't take them and measure the times in space and plot them and come up with a line that shows us where the source of those things might be because of this phenomena. And I hope that explains it. Now, on the other hand, if there had been muzzle blasts there, then we could have asked that simple question and we could have made the simple observation, because muzzle blast is proportional to the Euclidean distance, and the closer you are, the earlier you hear it. But not true with the supersonic crack. You could be out there almost twice the distance and still hear the supersonic crack first, because the bullet came extremely close to you. Alright, let's see if there's anything else I wanted to cover. No. Well, let's see, what do I have over here on this? Oh, yeah. Yeah, there was something else, but we've gone on long enough. I'll cover this another night. Alright, so that concludes this one. The next couple videos I'm going to do are still related to the sniper thing, and I'm going to cover why establishing a global timeline, number one, is so hard, but also it's kind of inaccurate. So I'm going to start going into how errors propagate in calculations and measurements to show why every statement that's made about Vegas must include a margin of error. And that's why I always state that with the current calculations that I do based upon lags and all that, then I can't identify the shooter's location more closely than 100 foot or so, simply because of the inaccuracy in some of the measurements. Most importantly, the locating the finite positions of the recordings, but also due to the fact that the nature of the calculations amplify those errors. So if I'm off by 50 feet in locating a video, which is not hard to do, then I could be off by 500 feet, or 400 feet anyway, in the final answer, because the nature of the calculation amplifies the error. Now, not all calculations amplify the errors. Some of them minimize them. And that's the type of algorithm you want, but you can't always find it to solve the problem. So anyway, I'm back. We're talking. There's complications in taking those sniper ones and just plotting it on the timeline and making any real conclusions. And I'll grab you in the next one.